Hey guys, welcome to Mini-URT number 4. Today we're doing another user requested Mini-URT on the topic of air stability and processes that occur in the atmosphere. So to begin with, the atmosphere is really just a big mass of air that coats the whole planet. You'll find that if you were to move up in the atmosphere, say for example in a balloon, that the temperature of the air as well as the pressure would decrease at a certain rate. This is known as the environmental lapse rate. Again, it varies from place to place, but you're looking at maybe a drop of 1 to 2 degrees every 500 meters that you head up. Now, importantly, this drop in temperature is not due to the exchange of heat, say, with space. This is actually what's called an adiabatic process, where you have a change in volume, which results in a drop in pressure, which in turn results in a drop in temperature. Now imagine we have a patch of ground that receives solar insolation and creates effectively a bubble of air that is rising up. More often than not, except perhaps in desert conditions, this bubble of air will contain evaporated moisture, but that moisture will effectively be dispersed. So the package of air can effectively be considered dry as it's rising up. And it will expand and cool at a certain rate, about 10 degrees every 1,000 meters, right? This is known as the dry adiabatic lapse rate. Now this is where an interesting phenomenon takes place. Once the temperature has cooled to a certain point, I think it's around 6 degrees, the water, the evaporated water that's in this package of air, start to coalesce. And as a consequence of the release of latent heat due to the coalescence of the water particles, the rate at which the parcel of air is cooling slows down. This is known as the saturated adiabatic lapse rate. Now remember that the environmental lapse rate is only about maybe 2 degrees every 500 meters or 4 degrees every 1,000 meters, put things into perspective, which means that this dry parcel of air that's rising is cooling faster than the environmental lapse rate. Now, when whatever it is that's driving this parcel of air, say for example solar insolation, stops, so the sun goes down, this packet of air that has been rising and cooling more rapidly than the environmental lapse rate settles down and begins to sink effectively. So in terms of the interaction, this is considered stable. Now, because we live in the real world, the environmental lapse rate isn't necessarily a constant 2 degrees every 500 meters. So imagine this situation. You've got a bubble of air that is experiencing adiabatic expansion, and it contains some moisture, and it is ascending at a rate that and cooling at a rate that ultimately should make it stable. But if it gets to a point where, say for example, it reaches saturation and begins to cool slower than it was when it was effectively dry. But the problem is that the environmental lapse rate is no longer what it was. The environmental lapse rate is now greater than it was on the ground. So as a consequence, this bubble of air continues to rise. Now this situation is inherently unstable and will continue to remain so as long as that package of air remains saturated. This is what is known as conditional instability. I hope this clarifies a little bit about what is described in chapter 4 of the textbook. Alright, see you guys at the next Mini-URT.